So, if you take a simple electron transfer reaction, it is little easy to understand, therefore, I am taking that example. We have CDL, which represents the double layer capacitance. We have a resistance to represent the reaction at a particular DC potential, and we have R solution. Right now, I am going to neglect that and say it is very small value or 0 value. And if I draw the complex plane plot for this circuit, I would get a semicircle. This is high frequency data and this is where the low frequency data will end. I will get a semicircle and the tangent here is going to be at 90 degree, that is pi by 2 radians, because we are assuming solution resistance is 0, and this semicircle has a origin on the real axis. Okay. But often when we do experiments, we find that even if you take a very simple reaction, we do not get a real semicircle. Instead, what we get is only a smaller part of a circle. Now, look at this, the starting point and ending points are still the same. On the real axis, it is still 0 here, and whatever value it is, let us say it is 100 ohms, it is going to be 100 ohm here, this is also going to be 100 ohms. But this is as if it is part of a circle which is pushed down, the center is pushed down. So, sometimes this is called as and for this, if you look at the tangent, even if the solution resistance is 0, if you look at the tangent, it is going to be little less than 1 pi by 2. So, we would write it as n pi by 2 n less than 1. So, the circle radius is not the same as what it was before. Previously, the circle diameter was RT, now the circle diameter is not RT, it is larger than that. So, this is still a fraction or a part of a circle, but it is not really half a circle, it is less than that. It is not that we are visualizing it as a arc like this, and this is what is experimentally seen many times. Okay. And this is represented by an element which is termed as constant phase element. Okay. So, there is a reason for that, I will explain that a little later. For this, if you calculate the impedance, you have to use two parameters. There are different ways of using this. Sometimes people write it as q j omega power alpha. Because we use alpha for charge transfer coefficient, we are not using it here, we will call it as n. Sometimes people use y0, sometimes people use y for admittance. So, we will have to have a compromise. Right now, I am just going to say y0 for the coefficient here and n for the exponent there. When n is the same as 1, this is going to be capacitance. We would write j omega c as the admittance for the capacitance, 1 by j omega c as the impedance for the capacitance. Here, notice that the j omega is within the brackets and it is raised to the exponent n. It is not 1 by this case, all the values are imaginary, just that how it changes with omega will vary. In this case, it is generally a complex number where n is not an integer. Okay. If n equal to 0, it is a real value. If n equal to 1, it is a capacitance. Okay. And the impedance is an imaginary number, not a complex number. You can say it is a complex number, but it is really an imaginary number. And if n equal to minus 1, it is going to be like an inductor, it is again an imaginary number for the impedance. N is 0.5, it is going to be a complex number, it has the real part and imaginary part. Okay. In general, it is going to represent a complex number there. Now, I want to show you how it looks like if I take the pure element and generate the impedance for various frequencies and plot it in Bode plot as well as in complex plane plot. Okay. So, I had taken this expression, that is ZCPE as 1 by y 0 j omega power n. I had taken some examples where I am plotting a double layer capacitance with 20 microfarads. It is just an artificial calculation, I mean artificial element, I am calculating it. So, now I am not writing it as per centimeter square, even here I should not have written this, but it is okay. Y 0, the units of y 0 has to be such that this comes as ohm or ohm centimeter square. So, y 0 will have a unit which depends on the value of n. Here I am taking n as 0.9. Okay. I am also plotting the impedance for an inductor of 10 Henry, impedance of a resistor, it is 100 ohm, it is always going to be 100 ohms. If I put it in a complex plane plot, this is the imaginary axis and this is the real axis, and this is sort of zoomed in version. Resistance is just going to be there 100 ohms regardless of which frequency we use. This is how the value will look like. If I really measure, it is going to just hover around that, because there is going to be some experimental noise. Okay. If I take a good capacitor and measure it correctly, high frequency is going to be here, lower and lower frequency it is going to become more and more in magnitude, but it is still going to be an imaginary number. Okay. If I take an inductor, it is going to start at 0 frequency, it is going to be 0. Inductor has at higher and higher frequency, it is going to have more values. Okay. And this is given in terms of 10 power 6. Okay. 1 mega ohm, 0 to minus 1, 0 to plus 1 mega ohm, 0 to, or actually it is going from I think minus 0.1 to 1.9 mega ohms. Mega ohms or mega ohm centimeter square, we will sort it out. If you look here, the red color line corresponding to 0.9 of the CPE, it is actually going at a slight angle to this. When n equal to 1, it is a capacitor, it is going vertically. If n equal to 0.5, it is going to go as a 45 degree line. N equal to 0, it is going to go as a, not as a line here, it is just going to settle as a point. N equal to minus 1, it is again going like this. Not just that, notice the value, I have used 4 10 power minus 5 for the y 0 value, I used 2 10 power minus 5 for the capacitance, and yet if I look at the magnitude here, it is actually smaller at the lowest frequency, it is a smaller value. That means, you can't just take this value and compare with this value. It won't even give you an idea of how the impedance will be for a given frequency. You will actually have to calculate it with the n value. If you have 2 capacitances, you do experiments, you get 3 capacitance values at 3 different conditions, you can compare them and say something about it. Okay. If you get constant phase elements, sometimes with n equal to 1, sometimes with n equal to 0.95, another time with 0.98, another time with 0.92, you can't just take the y 0 values and compare them. It is not a fair comparison. Okay. Now, if you plot them in Bode plot with log of z, I have put the log scale here, okay, with frequency in the log scale. A pure capacitance will give me a straight line with a negative slope. Basically, I have to take this and take a log of this, I am going to get ln z or if I take the magnitude, the j will go away. This is what will look like. So, it is going to look like a straight line with a negative slope minus 1. If I take this as 0.9, it is going to look somewhat like that, but with a slightly lower slope. 0 of course, it is going to look like a 0 slope, this minus 1 is going to look like a plus 1 slope here, this n equal to minus 1. If you look at the phase here, capacitor is going to look like this, sorry, capacitor is going to look like this. This is actually 90 degree, this is going to be lower than 90, 0 and plus 90 degree here. This element has a constant phase. Capacitor also has a constant phase, resistor has a constant phase, inductor has a constant phase. This element does not have the same phase as any one of those, but otherwise its phase is constant, although the magnitude is changing. Okay, this is the reason it is called a constant phase element. Sometimes people call this behavior as frequency dispersion of capacitance. What they mean is, if you take a capacitor and calculate the impedance, okay, you can calculate the impedance based on the frequency. Okay. And if I tell you the impedance and tell you the frequency, you can calculate the capacitance. Okay. That means, if I give you various values here, at each value you can calculate the capacitance, and if I take the dark pink colored line there, I would get one value for capacitance. At each of this value I will get same value, each of these frequencies. If I take this, I can still assume this is a capacitor, and using this formula with n equal to 1, I can calculate the value of C, but that will vary as we change the frequency. That is essentially saying, if I assume that this is a capacitor and calculate the capacitance based on the impedance value and the frequency value, I will get a capacitance, but that is a function of frequency, that is not a identical value everywhere. That is another way of saying that it is a constant phase element. So, they would call, we see a frequency dispersion of capacitance. That means, we are not seeing a ideal capacitance everywhere, we are seeing a frequency dependent capacitance here, and that is essentially a constant phase element. Now, where do we see this and how does it occur? Okay. Usually this is seen when the electrode surface is rough, and initially researchers thought that that is because you have a rough surface, the double layer capacitance and the resistance keeps varying across the surface to a significant level. That is, you have millimeter level or multiple scales of roughnesses, millimeter level, micron level or nanometer level. People used to think that it may be caused because of rough electrodes in millimeter level or hundreds of microns level roughness. Microscopic roughness means the electrode appears to be more or less smooth even if you look in micron level scale, but individual locations have different energy levels. Energy level means, for a reaction to occur, if I have an alloy surface, let us say one of the elements promotes the reaction, other element does not promote the reaction, or it promotes to a lesser level, and if I have atoms surrounded by different atoms, it may promote to a particular level. Okay. But the surface may look flat. If I just use an AFM and measure the roughness, it may look flat, but this energy levels are different, meaning the reaction is catalyzed to a different level. That is a possibility. Okay. If I take a pure element and roughen it, again I will get different crystal planes, and they may again have different energy levels for promotion of a reaction. So, now the thinking is that it is caused by atomic level heterogeneity, not by macroscopic level heterogeneity. Although generally if you introduce macroscopic level heterogeneity, meaning if you make a rough electrode, the atomic level heterogeneity will also be there, in general that is true. Okay. And the way it is concluded is like this. So, you take a gold electrode, make it rough, clean it with acid, alkali, hydrogen peroxide. These things will usually remove material, it will not remove gold, but it will remove any other contaminant that may be present there, and conduct a simple electrochemical reaction and see how it behaves, and it will behave like a constant phase element, it will not give you a pure capacitance. Next, we can anneal it at moderate temperature, not very high temperature. If you go to high temperature, gold will melt. You go to less than 500, gold will not melt, but it will anneal, meaning some of the stress will be relieved, and to some level very small fluctuations, roughnesses will go away, but the major roughness will not go. So, if you take a SEM or AFM before annealing and after annealing, structural change in terms of the physical morphology will not be significant. But if you do a electrochemical experiment, at least they report that it behaves more towards an ideal capacitor. That means, initially if we say the roughness leads to an N of 0.7, 0.8, 0.9, somewhere in this range, depending on how rough the surface was, not really depending on how rough in physical sense, but in terms of the variation in the energy levels. After annealing and maintaining the same physical roughness, they get close to 0.9899 or somewhere in that region, and that leads to a conclusion that what you see here is because of energy level variation. Energy level variation is one way of saying that. Another way of saying that is that the current distribution is not uniform. If the reaction occurs at the same rate everywhere in the electrode, current will also occur at the same rate, assuming of course potential is also distributed evenly. Okay. If the rate is different at different locations, the current passing through at each of these regions, right, if you imagine that these are different islands, that is also going to change, and the proposal is that this is causing a CPE behavior. Of course, none of these are like really agreed upon by everybody, it is proposed that this is one possible reason. The other thing that one needs to notice, the Y0 value is not a capacitance. The CPE behavior can arise from different causes. In one case, it is a heterogeneous surface, it is 2D distribution. So, I just tried to plot it here or picture it here. You have a surface, this is hidden from the solution, only this top surface is visible to the solution, and I just shown it in different color to say that it is a flat surface, but these are actually behaving slightly differently in terms of electrochemical reaction. If it is identical, then I would just represent it by one capacitance here and a solution resistance here, that is all, there is no reaction here, and this is just another pictorial to say this is the surface atom, these are all below the surface, and out here they are not of the same color, they are different color, just to indicate that the pink color may be copper, the yellowish color may be gold. So, that is actually a heterogeneous surface, although it is a flat surface. Now, if I model this, I should probably model this with many different capacitance and resistance. This has a capacitance and this has solution resistance, this is the capacitance with solution resistance. So, various capacitance values here and solution resistance, that is a possibility. So, I should actually model it with many capacitance and resistance in parallel, I mean capacitance resistance unit in parallel. That would say when I send electrons from here, it is going through multiple paths here, and then it will be collected and pass through the potentiostat at the other end. You may have a simple electron transfer reaction, in which case you would get R solution, R T, and of course Y0 and N here. So, there are different proposals. In one proposal, solution resistance was not considered, and you can extract an effective capacitance from this. So, you obviously cannot use Y0 as effective capacitance, but you can use this formula to estimate the effective capacitance. How do we get the formula? I have not told you that yet. Yeah, it is another proposal to say that if solution resistance is 0, of course, these two are going to be matching, but when it is not 0, it have a slightly different formula. Yeah, go ahead. Which graph? No, this graph is for a case where you have a resistance. Okay. So, what I showed you earlier, I will just extend it a little more. Okay. I will say this is the origin, this is Z real minus Z imaginary. Pure capacitance, high frequency will start here, low frequency will go here, it is in the imaginary axis. Pure inductance will go like this, except that low frequency have low impedance, high frequency have high impedance. Pure resistance will just have one on the real axis, one point. A constant phase element with n slightly less than 1 will look like a capacitor, but it is going to be at an angle, it is a complex number. If I say there is a resistance and then a capacitance, or resistance and capacitance will start here and will have value like this. A constant phase element and a resistance will have starting point here, because even if I go to infinite frequency, I will get 0 impedance from this capacitance or from the constant phase element, but the resistance will be there, it is not going to be 0. Okay. So, resistance plus a constant phase element, resistance plus a capacitance will have lines here. It is still going towards infinity when I go to low frequency. This in parallel with the resistance will give me this, and in those cases I can use these two formula to extract an effective capacitance.
So, like we discussed in the previous slide that if we have different current at different points, so we can say there is a non-homogeneity exists, yes, and there will be a CPE will exist. So, can we say with this also, like copper and gold, they have different conductivity, different resistivity. So, maybe we
conductivity is more or less, I mean at this level the conductivity difference is not really significant. Meaning we are measuring few ohms, few milliohms, etc. Yes, there is a difference in conductivity, but that is not causing. When we have copper wire, aluminum wires, little longer wire, shorter wire, by and large you will not see much difference in the impedance measurement. Only in special cases, even then it is not that it is pure copper or mixture of copper and aluminum, any of those things that is causing the problem. When it is exposed to solution, it is not the conductivity of this and this that is causing the difference, it is the reactivity that is causing the difference. Yeah, go ahead please. Yeah, here, which one, the one on the complex plane or the one on the Bode plot?
On the complex plane.
Complex plane, the red color dashed line is the CPE, the violet or dark pink color is the capacitance. Of course, I wanted to show you in equal scale, therefore, I have plotted like this. If you zoom in more and more, you would see a difference. No, one is at a slight inclination. Look, the dark pink color line is a straight line, vertical line. Both are straight lines, that is correct, but both are not vertical lines. This red color line is a straight line, but at a slight angle to the vertical. Okay. In fact, that is what is given by the previous slide. The vertical line it is at pi by 2, this is 0.9 pi by 2. Of course, you can get into degree, pi by 2 is in radians, this is at a slightly lower angle. If you put it in equi-scale, this may not appear that well. If you zoom in and put different scale, you might see the difference better. Another way to look at it is this, look here, you would see a difference. Magnitude, of course, there is a difference, phase also, but magnitude I can choose a different value of y0 and make it come closer, even closer than this. Phase value will not change. So, these are obtained using the following method. If you take a regular Randall circuit and plot this in complex plane plot, you can relate the peak here, peak value here, meaning not the imaginary and real value, at what frequency do we get the maximum here. From that you can calculate the capacitance. If you change the capacitance, you have done this in the exercise, if you change the capacitance without changing the solution resistance and the charge transfer resistance, the points here will move, although the line, entire line will not appear to change. Points there will move, and if I mark the frequency at which the maximum occurs, I can find capacitance from that. So, there is a way to extract the capacitance by looking at the maximum value here. Okay. I can do similar thing in impedance, I mean I can do the same thing in admittance format also. Okay. Meaning admittance, it is going to look like, it is going to, if it is a fixed value here, it is going to be fixed value here, another fixed value here, and I can look at the maximum value, maximum or minimum, whichever that is, and then say that can be used to relate to the capacitance. In case of CPE, obviously this is not a semicircle, but you can still take the maximum, and if you say in CPE the maximum can be related and we can extract the capacitance, this is how you would get the capacitance value. In admittance form, one of the equation would come, in the impedance form the other equation would come, but basically these are taken by using the procedure which we normally use to take peak value and extract the capacitance from that. Of course, now we do not do this, right, we can fit it using a software. Previously what people would do is, when they do not have access to such programs, they would plot it, get the R solution by extrapolating in the graph, get the RT by marking where these points will go, and then go to the center meaning the peak value, note which frequency that point is, and from that they will calculate the capacitance. Now we would use the software, use optimization and then get the value, because we can fit it to many types of circuits, but this is the origin of this equation. However, I also want to note the following: if you just take many resistance capacitance in this form and randomly assign values, here what I had done is I used a fixed resistance value everywhere, but randomly change the capacitance value, randomly meaning I had taken it such that it varies between 20 . So, I had taken a standard deviation of 6 microfarad, average of 20 microfarad and 3 sigmas as the limit. So, I have allowed it to vary randomly. So, what I had done is taken one unit, divided into 10,000 units. Resistance also of course changes, it becomes much larger, so that they are in parallel, it will still give you the original resistance more or less. If I use the random distribution and plot it, first of all note that these are not equal scale, this is 0 to 30, this is 0 to 10 mega ohm. Okay. If it is a pure simple resistor with a simple capacitor, this is how it has to look. It has to start at 30 ohm and just go as a vertical line. A CPE behavior would go like this. Here you see it actually goes like this. It moves to the right and then goes up. Okay. What that means is, if I have random distribution of resistance and capacitance here, I will not get a CPE behavior. So, when we say atomic level heterogeneity is there and the resistance and capacitance vary, they are not identical, therefore, we are getting a CPE behavior, we are not going to really get that, because if you look at the phase here, I generated this spectrum and then look at the phase, it is not, this is supposed to correspond to minus pi by 2, minus pi by 2 if it is pure capacitance. If it is CPE, it is going to be little less than that, but it is going to be flat everywhere. Instead, I get a distribution like this, it is varying from minus 1.6 to minus 1.35, and that does not give me a CPE behavior. So, there is a proposal, Varism and AAA's book tells that a particular type of distribution gives rise to CPE behavior, and that is basically a Gaussian distribution, not in terms of the capacitance, but in terms of ln tau. Tau here is the time constant corresponding to each R and C. So, the resistance and capacitance can vary, and that together is called variation in tau, and that tau distribution has to be in a particular form, only then you would get a CPE like behavior. So, we can't just say that randomly these vary and then they will get a, or uniformly they are varying. You can't assume any particular distribution other than what is proposed there, because only that I have not tested it, but I am just taking it on face value that only a particular distribution will give you the CPE behavior. Of course, when we experimentally prepare, we see this, we are not somehow preparing in that distribution. Okay. So, that is a proposal to say that that can give rise to the CPE behavior. What it means is there is no universal clean explanation universally agreed upon by everybody to say you get CPE behavior because of this. There are proposals, there are some cases where you can eliminate the possibility, we can eliminate the possibility that a random distribution of capacitance and resistance will give rise to CPE behavior, and with experimental error that might appear somewhat similar to this, but it is not going to look like a clean CPE if you are preparing it in a random manner. Okay.
So the objective is to basically tell all those 5 sets of resistance capacitor can be modeled as one resistance in one CPE.
Yes.
And that resistance will be the same as all the resistances, or
No. See, if you take 2 resistance in parallel, the effective resistance is going to be half of that, right? So, it is not going to be the same as that resistance. If I distribute into 10,000 resistances, I would say that each resistance is 10,000 times the original final value that I am looking at. If I say one resistance, one CPE is final model, right, and I think the resistance is, for example, in this case I have taken it, right, it is artificial, I have synthesized it. So, I say 100 ohms as the resistance and 20 microfarad is the capacitance I am looking at, but it is a CPE. So, it may be 25 with the proper unit and then 0.95 or so. What I am doing here is to take 100 ohm multiply by 10,000. So, each resistance is going to be a large resistance, but when I have many large resistance in parallel, I am going to add the admittance of these to get the effective admittance, right. In this case, of course, I am going to add the admittance of this unit, not just the resistance, but each resistance is not going to be the, if this is the value, let us say this is 100 ohm and I have taken this, in this example I have taken 10,000 such elements, I would start with 10 mega ohm for each or 1 mega ohm for each. So, this is 1 mega ohm, this is 1 mega ohm and so on. If I have 10,000 such elements, assume just right now imagine the capacitance is not there, I will have to use much larger, right, I can't use the same number.
if like how is the mapping done with capacitance being there? You map this system to this system.
I have taken up resistances, many resistances and taken up many capacitance values, but assuming I want to get around 25 or 20 or 30 ohms and I am going to prepare n number of them, right, I decide how many numbers I am going to use. So, I choose or I chose 10,000 numbers, I am actually recalling from memory, I do not remember exactly what number I chose, but somewhere around that, okay. 20 or 25 ohms for the final value, that means I have to choose 25 into 10,000. Okay. Capacitance values you can again calculate, right. For the capacitance, if I want, if I am expecting 20 microfarad here or something equivalent to that, right, in the CPE. Now, I will not expect 20 microfarad in the CPE, I will expect some equivalent value there. I would divide this into 10,000. So, 2 microfarad by 1000, 2 nanofarad each. If I use exactly 2 nanofarad each, then there will not be any CPE distribution, because resistance is uniformly distributed, the capacitance is also uniformly distributed. So, all that I need to do is this is 1 mega ohm plus 2 nanofarad, take that element and then say that that is, I will calculate the impedance or admittance, add the admittance or multiply that by 10,000 times, I will get the final admittance. So, that is going to be proper resistor plus a capacitor, that is all. Whereas, if I say either the resistance or the capacitance is distributed or both are distributed, meaning on the average I am going to use 2 nanofarad, but I am actually going to go from 0.2 to 3.8 nanofarad. Randomly I am going to vary that. On the average it is still going to be 2 nanofarad. Then what I get is this.
1000.
Yeah, it is okay. We will get the same result.
It will get changed now in that case.
No, not very different. If you use 2 elements versus 20 elements, there is going to be a difference. If you use 100 elements or 1000 elements, you are not going to see much of a difference. I just use 10,000 because it is for sure that is large enough number of distributions.
So, can we say that by doing this calculation, we get a different value from we are going to measure it by manually we are going to measure that point?
The point of this exercise was to show a random distribution of R and C will not give you a CPE behavior. So, if you use 10,000 or 1000, I do not think it is going to make a difference. If you use 1000 or 100, it will look little more grainy. If you use 100 or 10, probably there will be more grain in that, in the sense this looks smooth, right. It will probably look somewhat like this if I use fewer elements. If I use 5 elements, it will not be that nice, but then 5 elements is not really a good way to say it is very heterogeneous surface with, for the picture it is okay. I had to draw some pictures, so I showed 3 or 4 islands, but that is not what I really mean when I say it is heterogeneous. I mean there are many and they are not randomly distributed, that was the point. If you use actual measurement, you will get a CPE behavior. All this information here is to see whether we can get the CPE behavior by using some circuit. Then we can say okay, probably this is the origin of the CPE behavior, and the general idea is yes, this seems to be the origin of the CPE behavior, but this is not coming from random distribution. Now, I have not created this distribution and verified it yet. That is why I am not able to tell with confidence that if you have many such elements, but where the RC values are distributed in this particular way, you will get a CPE behavior. In order to do that, I should create it, simulate it, and then show that it goes like this. I have not done that yet, but that is what is proposed in literature. So, I am showing it to you, informing you that this is the proposal. It is probably correct, but I can't say with confidence, but definitely the random one will not give you, that I can say with confidence. It is also possible to get a CPE behavior with what is called 3D heterogeneity. Imagine you have a film, okay. From one location to another location you may have a difference in the film, or you may not have a difference. In the film itself, when you go from the electrode to the solution, the properties can change, composition can change. So, that is what I have tried creating here. One is to say location to location you have difference, that is a possibility, but within a location if it is completely uniform, another location it is a different color, but again uniform, that is still you can consider it as a 2D heterogeneity, because only when you move from one location to another location you see a difference, but if you move vertically in the third dimension there is no difference. But what is shown in the pictorial representation here is if you go in this direction there is a difference. If you go on the surface, of course in the picture I will show only one line, but if you imagine there is an electrode on the surface, if I move at a given location in the height, still you can see a variation. Then this itself you have to represent by a CPE in parallel with the resistor, and still we are assuming there is no reaction. So, this also gives rise to a CPE behavior. Of course, you are starting with this. So, even if you have only one, it is going to show you CPE behavior. This mixture will show you a CPE behavior, and in a pictorial level I tried representing this by CuO. Of course, CuO means there is going to be larger molecule, but here I just showed it like similar sized ones with different color, dark green, light blue and pink color. Pink color is copper, one type of oxide, another type of oxide. You see a height variation, you see a composition variation. This can also give rise to a CPE behavior. There is one more factor, and with that I will stop. The admittance is given by y 0 j omega power n. Mathematically they are two independent values, you are fitting it and you are finding y 0 and n. But actually if we take a system, get the CPE value by doing the impedance spectroscopy and fitting it to a circuit, change it slightly, maybe different DC potential, different solution, slightly different solution, you get another CPE value, or maybe roughen the electrode and get the CPE value, you will find that the y 0 and n values are not completely unrelated, they are not independent. I am not saying take gold electrode in sulfuric acid, take copper electrode in potassium hydroxide and compare them. Even there you might be able to compare, but take one system and find some variation there, either potential or composition, you would find basically it looks like same electrode, same solution with slight change. You will find that they are related. When n value decreases, y 0 value will increase. Y 0 unit of course should be in similar scale. If you write ohm inverse, centimeter inverse, s power n, you should write all of them in the same way. If you write it in kilo ohm, you should write in the same way. But s power n, n will vary. It is going to be 0.9, 0.95 etc. depending on what the exponent is. But if you plot them as the value of what is shown as alpha here, that is n, decreases, value of the CP exponent, not exponent, the pre exponent y 0, what we call as y 0, what they call as q, that increases. That means they are related, they are not completely independent. Okay, we will stop here today.